Greetings. My name is Dr. Elma Chibiza. So today I'm going to be taking you for chemical bonding. Let's continue. So the prerequisites for our course, ideally the students should have covered the first 20 elements of the periodic table, and also they should have covered our introductory lecture in chemistry so that they'll be able to grasp the tenets of chemical bonding. So this is the periodic table. As you can see, the periodic table consists of metals, which are to the left of the periodic table, and non-metals are to the right of the periodic table. There is a demarcation which separates the metals from the non-metals. It is made up of what we call metalloids. So the metalloids basically consist of boron, silicon, germanium, arsenic, antimony, and tellurium. So as you can see, to the left, it's mostly the metals, but to the right is the non-metals. There is an exception, however, of hydrogen, which is found to the left of the periodic table. And we shall see with the properties of hydrogen how it also resembles metals in as far as its reactions is concerned. Chemical bonding. Basically, it refers to the forces that holds atoms together in molecules, ions, and other species. There are three main types of chemical bonding, namely ionic bonding, covalent bonding, and coordinate or rotative bonding. So let us delve deep into the three types of bonding. Right, ionic bonding. This is a bonding which is due to the transfer of electrons from a metal to a non-metal. This transfer of electrons will result in an electrostatic force which keeps the compound together. Examples of ionic bonding, we have sodium chloride, magnesium oxide, and magnesium chloride. So let us show how this metallic bonding comes into being. Right. So we are going to use the example of sodium chloride. Okay. Right. So from the periodic table, we can see that the mass number of sodium is 23 and its atomic number is 11. Similarly, the mass number of chlorine is 35 and its atomic number is 17. So if the atomic number of sodium is 11, it means that it also has got 11 electrons because this is a neutral atom. Similarly, with chlorine, it also means that it has 17 electrons because it is a neutral atom. We now want to draw the electronic structures of sodium and chlorine to see how ionic bonding comes into being. So this is our sodium. It has got 2 electrons in its innermost shell. Okay. Right. This is how we represent the structure of the sodium atom. Okay. The innermost shell has got 2 electrons. This outer shell has got 8 electrons. It has reached the octet state. And the outermost shell has got 1 electron. Similarly, we proceed now to draw the structure of the chlorine atom. Okay. This is our chlorine. Right. The innermost shell has got how many electrons? 2 electrons. Okay, so we are going to represent the electrons of chlorine as dots, since we have represented the electrons of sodium as crosses. Okay, right. So it has got 2 electrons in its innermost shell. This outer shell has got 8 electrons. Okay, we now at 10, but you know that it has got how many electrons in the outer shell? It has got 7 electrons in the outer shell. So we have got 2 here, We have got another 2 here. We have got another 2 here to make 16. So the other one is here, right? So with ionic bonding now, sodium, the metal, is going to transfer an electron from its outermost shell to the chlorine atom outermost shell. Right. So when it does this, it means the sodium atom now has 8 electrons in its outermost shell, and it has attained stability. Okay. Similarly, chlorine now has 8 electrons in its outermost shell. It has attained the octet state, and it has now attained stability. So therefore, we are going to have a sodium okay, and a chlorine atom here. Right. So chlorine. Right. So this sodium now has got a maximum of 10 electrons. Therefore, it is going to attain a positive 1 charge. This chlorine atom here now has 8 electrons in its outermost shell, meaning it now has 18 electrons, okay, against how many protons? 17 protons, because its atomic number is 17. So it means that this has now attained a negative 1 charge. So this is how ionic bonding comes into being. Okay, so there is the transfer of an electron from sodium, which is our electropositive atom, to chlorine, which is our electronegative atom. So what keeps these atoms now, what holds these atoms together are strong electrostatic forces emanating from this positive charge and that negative charge. So this is how ionic bonding comes into being. Similarly, you can also draw the electron dot diagrams for magnesium chloride, for magnesium oxide, as you practice how ionic bonding comes into being. Okay, so let us proceed. Right. So that diagram there also represents ionic bonding. So from the illustration which we have made previously, it means you can now follow and draw electron dot diagrams to illustrate ionic bonding. Secondly, we have got what we call covalent bonding. So with covalent bonding now, this results from the sharing of electrons to achieve stability, okay, or a full electron shell in the what? In the outermost shell. So examples of covalent bonding, we have got water molecule, we've got the chlorine molecule, we've got hydrogen chloride, we've got carbon dioxide, we also have got methane and ethane. Okay, so this illustration here is showing how covalent bonding is in a water molecule, right? So if we look clearly here, we've got a hydrogen atom, okay, whose electrons are represented by these dots, okay. These dots here are representing the electron from hydrogen atom. So we know that hydrogen has got an atomic number of 1, and it has got 1 electron in its outermost shell. For oxygen now, we know that the atomic number of oxygen is 8, meaning that it has got 6 electrons in its outermost shell. Right. So these crosses now are representing the number of electrons which are in the outer shell of oxygen. So we have got 2, 3, 4, 5, 6. There are 6. Right. So what happens is that hydrogen will then come with its 1 electron here, and another hydrogen atom will come with its 1 electron here. So what would have happened is the oxygen atom has now attained stability. It has reached the octet state. And similarly, the hydrogen atom has also reached stability by reaching the duplex state. It now has got 2 electrons in its outermost shell here. So we have now obtained a covalent bond, right? So this is easily illustrated by an electron dot and cross diagram to show how the sharing of electrons is all about. Okay, so we can proceed to draw electron dot diagrams for the chlorine molecule, for hydrogen chloride, for carbon dioxide, for methane, as well as for ethane. Now we proceed to a special type of covalent bonding, as we have seen here. In this covalent bonding, one atom is providing an electron for electron sharing in the covalent bond. However, we've got another type of covalent bonding which is called dative or coordinate bonding. In dative or coordinate bonding, we have got one atom contributing all the electrons which are shared in the covalent bond. Right. So coordinate or dative bonding is exemplified by the structure of boron trifluoride and ammonia. Okay. Also boron trichloride and ammonia. Right. So I will use the illustration of boron trichloride and ammonia here. Right. So when we look at this nitrogen atom, we know that the atomic number of nitrogen is 7, meaning it has got 5 electrons in its outermost shell. Hydrogen, as we have seen previously, it has got 1 electron in its outermost shell. So each hydrogen atom will come and bond covalently with the nitrogen atom here, meaning that we'll be having 2, 4, 6 electrons, right? This 1 electron from nitrogen, another electron from hydrogen, 1 electron from nitrogen, another electron from hydrogen, and also 1 electron from nitrogen and another from hydrogen, to come up with 6 electrons here. So what it means is, out of the 5 which are in the outer shell of nitrogen, we have used 3 here to form covalent bonds with hydrogen, right? So we are left now with a lone pair of electrons on the nitrogen atom. Okay, that is the structure of ammonia. We have got a lone pair of electrons on the nitrogen atom. Right. Now, let us see the structure of boron trichloride. Right. So for boron trichloride, we know that the atomic number of boron is 5, meaning that it has got 3 electrons in its outermost shell. So as it has got 3 electrons in its outermost shell, what it means is all the 3 electrons now are going to participate in bonding by sharing electrons with the what? Chlorine atom. So 1 boron electron will share with 1 chlorine atom. So we've got 1, 2, 3, and it has exhausted all its electrons. However, when we look at the boron now, it has not attained stability. It has not reached the octet state. It only has 2, 4, 6 electrons, which means it is deficient of a pair of electrons. So what happens in covalent or in this type of covalent bonding, which we call dative or coordinate bonding, is this nitrogen atom with its lone pair of electrons will come and share that lone pair of electrons with what? With the boron trichloride. So much so that the boron will attain an octet state stability by sharing these electrons, which are with what? With the nitrogen atom in ammonia. So when you are representing this diagrammatically, it means that you have to draw this arrow here pointing from where the electron pair is emanating from towards the molecule which is being shared with this electron pair, right? So this is dative or coordinate bonding. Another important example of dative or coordinate bonding is seen in the dimerization of aluminium chloride, right? So this is your aluminium chloride. So aluminium, instead of existing as aluminium chloride LCl3, it does not exist as such. Instead, it exists as a L2 Cl6, right? Di means two. Mer, ma, it means structure. So by dime, it means it exists as a two structure, meaning that this aluminium here, if you look at it closely, aluminium, we know it has got an atomic number of 13, which means it has got 3 electrons in its outermost shell, right? So when aluminium bonds with chlorine, it will be a covalent bonding in which it will be sharing its outermost electrons with a chlorine atom. So when this electron from aluminium shares with this electron from chlorine, we can see that chlorine has attained stability. All the chlorine molecules here now, we have 8 electrons in their outermost shell and they've attained stability. But when we look at aluminium now, it only has 2, 4, 6, okay? So because it has got 6 electrons only, it means it's not stable. Therefore, it has got a tendency of attracting lone pairs of electrons which are available so that it completes its octet. So aluminium, it will do that by attracting a lone pair of electrons from this chlorine atom here so that it also reaches the octet state. So by so doing, we have 2 atoms of aluminium chloride existing together. And that structure of 2 molecules of aluminium chloride existing together is what we call a dimer. And the process or a phenomenon is called dimerization. So the dimerization of aluminium chloride is an important phenomenon which comes into being due to the effect of coordinate or dative bonding. Right, we now move on to metallic bonding. So basically, the metals consist of giant structures of atoms arranged in a regular pattern. The electrons in the outer shell of metal atoms are delocalized and so are free to move through the whole structure. The sharing of delocalized electrons gives rise to strong metallic bonds. So this is the structure of metallic bonding. As we can see, we have got delocalized electrons here, which are in the metallic structure. Okay, so as we look at the properties of metals now, we shall see how metals are very good conductors of electricity because of the presence of these delocalized electrons, which are capable of moving in an applied potential difference. Right, we now look at shapes and bond angles. Right, initially, we've got what we call the trigonal planar. An example of the trigonal planar, we've got boron trifluoride. So the bond angle for trigonal planar is 120 degrees. As we can see, the fluorine atoms, they are arranged in such a way that they are equally distributed surrounding the boron atom, right? So as we can see, this is a single plane which forms an equilateral triangle. So the bond angle in a trigonal planar structure is 120 degrees, right? So from trigonal planar, we then move on to the next structure. The next structure is tetrahedral, which is exemplified by methane, and the bond angle is 109.5 degrees. So as you can see, the molecule is a tetrahedral shape with the carbon atom at the center and the 4 hydrogen atoms at the corners of a regular tetrahedron, as exemplified by this diagrammatic representation. So the bond angle here is 109.5 degrees. We now move on to the pyramidal, right? This is the pyramidal structure, okay? This is the pyramidal structure. As we can see, it's exemplified by ammonia, okay? The difference between a pyramidal structure and a trigonal planar is in a pyramidal structure, there is a lone pair of electrons, whereas in a trigonal planar, exemplified by boron trifluoride, if you remember, we only have 3 fluorine atoms against 1 boron atom, and the bond angle was 120 degrees. But now, because of the presence of this lone pair of electrons, you can then see that the bond angle is now 107 degrees. Right, we have got what we call a linear structure. This is exemplified by carbon dioxide. As you can see here, the bond angle is 180 degrees. So the molecule has a linear shape with the carbon atom at the center and the two oxygen atoms at opposite ends of a straight line. Hence the bond angle 180 degrees. We have got another shape which we call nonlinear or bent, as exemplified by the water molecule. Okay, as you can see, we have got two lone pairs of electrons on the oxygen atom, and the two lone pairs of electrons on the oxygen atom gives rise to a bond angle of 104.5 degrees. When you remember the structure for ammonia is called the what? The pyramidal. And the structure for ammonia, it has got two lone pairs of electrons on the nitrogen atom. And because of those two lone pairs of electrons on the nitrogen atom, the bond angle, we saw it as 100 what? 107 degrees. But the water molecule now, with the two lone pairs of electrons, it means it is repelling further these hydrogen atoms. So because of that, the bond angle is going to be less than 107, and it will be 104.5, as we can see here. Then we have got the octahedral, exemplified by sulfur hexafluoride, okay? Hexa 6, okay? So it's called hexafluoride because it has got 6 fluorine atoms bonded to a sulfur atom. This is from grade 7 stuff, whereby we say the shape with 5 sides, it's a pentagon, a shape with 6 sides, hexagon, 7 sides, heptagon, 8 sides, octagon, 9 sides, nonagon, and 10 sides, decagon. So all those concepts, they also apply here in the naming of these chemical structures. So as we can see with sulfur hexafluoride, the bond angle is 90 degrees. The sulfur atom is bonded to 6 fluorine atoms, as exemplified in this diagrammatic representation. So this summarizes now the shapes of the molecules, the number of bonding pairs, the number of lone pairs, the diagram, the bond angle, and examples. Right, so we begin with linear shape. It has got 2 bonding pairs, right? And it has got no lone pairs of electrons. And the diagram is represented there with a bond angle of 180 degrees. Then we move on to trigonal planar. 3 bonding pairs. It has got no lone pairs. And the structure is exemplified as projected here. And the bond angle is 120. Examples include boron, trifluoride, trichloride. Right. We also have got tetrahedral. It has got 4 bonding pairs, no lone pairs, and the diagrammatic structure is as represented here with a bond angle of 109.5 degrees. Okay. We also have got the trigonal pyramidal with 3 bonding pairs and 1 lone pair of electrons. Right, the bond angle is 107 degrees, as exemplified by ammonia. We also have got a bent structure with 2 bond pairs and 2 lone pairs of electrons, and the bond angle 104.5 degrees. We also have got the trigonal bipyramidal, which has got 5 bonding pairs, no lone pairs, and the bond angles we've got 120 and 90 degrees. It is exemplified by phosphorus pentachloride. Okay, right. And we also have got the octahedral shape, which has got 6 bonding pairs, no lone pairs, and it is also represented by sulfur hexafluoride with a bond angle of 90 degrees. So it is very, very important for chemistry students to master these bond angles and the shapes, and also to see how the presence of lone pairs of electrons are contributing to the bond angles in these structures. We now move on to the bonding summary, okay, by looking at their properties, right? We are going to look at the boiling and melting points, conductivity when solid, conductivity when molten, as well as the general description. So for simple covalent, the boiling and melting points, they are low because of weak intermolecular forces between the molecules. Conductivity, because simple covalent structures do not have ions which move in an applied potential difference, they are poor conductors of electricity, both in the solid state and in the molten state. And these simple covalent structures are mostly gases and liquids. For ionic substances, okay, or ionic compounds, generally they've got a high melting and boiling point because of the lattice giant structures of ions with strong forces of oppositely charged ions, right? Their conductivity when solid, they are poor because the ions cannot move in an applied potential difference when in solid state. However, when in molten state now or in solution, the ions are free to move in an applied potential difference, thereby becoming good conductors of electricity. So basically, these ionic compounds are exemplified by crystalline solids. We then move on to giant covalent structures. Right, boiling and melting points. Generally, they've got high boiling and melting points because of many covalent bonds between atoms in a giant structure. Their conductivity, when solid, is poor, mostly for diamond and sand, because the electrons cannot move in an applied potential difference. However, we've got exceptions. For example, graphite, which is a good conductor of electricity. Why? Because it has got free delocalized electrons in its lattice structure, which can move in an applied potential difference, thereby becoming good conductor of electricity. Conductivity, when molten, is generally poor, and giant covalent structures are mostly solids, exemplified by diamond, sand. Now we go on to the metallic. Right, boiling and melting points. High strong electrostatic forces between positive ions and delocalized electrons. Okay, so the boiling and melting points are very high due to the strong electrostatic forces between the positive ions and the sea of delocalized electrons. The conductivity when solid is good because the delocalized electrons are free to move in an applied potential difference. Conductivity when molten is also good because they can move in a what? In an applied potential difference. And the examples of these metallic structures, it's mostly the shiny metals. We are continuing with our atoms and molecules. Right, sigma bond. So generally, a sigma bond is formed due to direct head-on overlap of atomic orbitals along the internuclear axis. So this diagrammatic structure here represents the formation of a sigma bond. As we can see, it is due to direct head-on collision of the atomic orbitals along their internuclear axis. There is also what we call a pi bond. There is also what we call a pi bond. Okay, so this is a pi bond. Generally, a pi bond is formed by the sideways or lateral overlap of an or the parallel overlap of an hybridized p orbitals. The diagrammatic structure here represents a what? A pi bond. Okay, it represents a pi bond. So the overlap of two p orbitals on each carbon atom forms a pi bond above and below the plane of the molecule, right? So we have got a pi bond above and below this molecule, thereby giving rise to a what? To a pi bond. Okay, so as we'll see, as we proceed, there are properties associated with sigma bonding, and there are also some properties associated with what? With pi bonding. But what is important in this stage is to know that a sigma bond is due to head-on overlap of the what? Of the orbitals, whereas a pi bond is due to lateral or sideways overlap of the what? Of the orbitals. Now, electronegativity. Electronegativity is the relative tendency of an atom in a covalent bond in a molecule to attract electrons in a covalent bond to itself. Electronegativity is measured on the Pauling scale, and the Pauling scale ranges from 0 to 4. The most electronegative atom or element is fluorine, okay? And it is given a value of 4 on the Pauling scale. So the factors affecting electronegativity, we see that electronegativity increases across a period as the number of protons increases and the atomic radius decreases. So as we move across a period, okay, the proton number or the atomic number will be increasing, whereas the electron shells will be remaining, the number of electron shells will be remaining constant. If we are considering period 3, the electron shells will remain constant at 3. However, the increase now in the atomic number or the proton number will mean that the positive charge, which is pulling the electron shells towards the nucleus, are increasing as we move. Therefore, the atomic radius is going to reduce. So as we move across period 3, we see that the electronegativity increases because the atomic radii will be decreasing, right? So radius is the singular form, radii is the plural, okay? Also, electronegativity decreases down a group because the distance between the nucleus and the outer electrons increases, and the shielding of inner shell electrons also increases. Right. Van der Waals forces. These are weak distance-dependent electrostatic attractions between uncharged or neutral molecules. We have got various types, which include permanent dipole-dipole, induced dipole-dipole, London dispersion forces. So permanent dipole-dipole forces, they occur between polar molecules. Polar molecules generally have a permanent dipole. And examples of polar molecules have got carbon and chlorine, carbon and fluorine, carbon and bromine, hydrogen and chlorine are examples of polar molecules. Polar molecules, they are asymmetrical and they have a bond where there is significant difference in electronegativity between the atoms. So what happens is one atom will assume a partial positive charge and another a partial negative charge, leading to a permanent polarity in the structure of the molecule. Right, permanent dipole. As we have seen in the previous slide, okay, this is an example of a polar molecule, hydrogen and chlorine. So hydrogen is going to assume a partial positive charge, chlorine a partial negative charge. So there is a permanent dipole which exists in hydrogen chloride. So polar covalent bonds, you have an equal distribution of electrons in the bond, and this now results in the separation and also a partial positive charge in another and a partial negative charge in another. And that phenomenon of having a partial positive charge and a partial negative charge in the two atoms in the molecule gives rise to a phenomenon which we call bond polarity. We now look at induced dipole-dipole interactions, okay, which can also be called London forces, right? So these occur between all molecular substances and noble gases. They can also be called London forces. In any molecule, the electrons are moving constantly and randomly. So as this happens, the electron density can fluctuate and parts of the molecule become more or less negative. That is, small temporary or transient dipoles will form. These temporary dipoles can cause dipoles to form in neighboring molecules, and these are what we call induced dipoles. So generally, an induced dipole will be of an opposite sign to the original dipole, leading to induced dipole interactions. So the main factor affecting the size of induced dipole-dipole interactions, the more the electrons in the molecule, the higher the chance of temporary dipoles formation. Therefore, induced dipole-dipole interactions are stronger between the molecules, and so the boiling points will be greater. That also explains the increasing boiling points of the halogens as we move down group 7. Okay, and it also explains the reason why in group 7 fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. It's all due to the presence of induced dipole-dipole interactions. Hydrogen bonding. So basically, hydrogen bonding occurs in molecules where there is a hydrogen atom which is bonded to one of the 3 electronegative atoms. So the 3 electronegative atoms which we have got nitrogen, oxygen, and fluorine. And remember from the previous slides, we said the most electronegative atom is fluorine, okay, which has got an electronegativity rating of 4 on the Pauling scale, right? So whenever we have got the formation of a bond between the hydrogen atom and any of the 3 electronegative atoms, there arises what we call a hydrogen bonding, right? So the large electronegativity difference between hydrogen and each of the oxygen, nitrogen, and fluorine atoms is what gives rise now to hydrogen bonding. So hydrogen bonding is exemplified by a water molecule. If you look at a water molecule, we know the molecular structure of water, H2O, 2 hydrogen atoms to 1 oxygen atom. And we have seen that the reason why water has got a bent structure is because of the 2 pairs of lone electrons, okay, which are present in the oxygen atom, right? So basically, the oxygen atom is going to become to get a partial negative charge, whereas the hydrogen atom will get a partial positive charge. So what will happen is that if this hydrogen atom has got a partial positive charge, it is going to attract a lone pair of electrons, which is in the next hydrogen molecule. So what will happen is that the bonding which forms between this hydrogen, which has got a partial positive charge, and this oxygen with a partial negative charge emanating from the lone pair of electrons is what we call hydrogen bonding. And hydrogen bonding is what explains some of the properties of water, for example, the cohesion of water, as well as the lattice structure of water molecules when frozen. So thank you very much. We have come to the end of our lecture, and I hope we have enjoyed this chemical bonding. So chemical bonding, it forms the foundation in chemistry, and it is very, very important for students to understand this chemical bonding as we move on to the next topics. Thank you very much. Take care.